Some equations look intimidating, mixing different bases and exponents, but often a hidden symmetry unlocks a beautiful and simple solution. Let's tackle this beast. 8 to the power of x plus 2 to the power of x equals 130. Before we dive into the algebra, let's see what we're dealing with. We can think of this as finding where two functions intersect. The first function, y equals 8 to the x plus 2 to the x, is this incredibly fast-growing blue curve. The second is just a horizontal red line, y equals 130. As you can see, the steep curve crosses the line at exactly one point. Our mission is to find the precise x-coordinate of that intersection. This visual check gives us confidence that there is one and only one real solution. So, let's find that solution. We start with our equation. Here's why we can't just take the logarithm of both sides. The logarithm of a sum is not the sum of logarithms. Log of a plus b does not equal log a plus log b. So we need a different approach. But here's the beautiful insight. Look at these bases. 8 and 2. There's a hidden relationship here that will crack this problem wide open. Of course, 8 is just 2 cubed. So we can rewrite the equation like this. Now we can use a fundamental rule of exponents to simplify this term. A power raised to another power means we multiply the exponents, so we can swap their order. And now the hidden structure is revealed. Look at that! The entire equation is built from a single repeating block, the term 2 to the power of x. This is the moment the problem cracks wide open. This repeating block is our cue for a substitution. This is the key insight. When you see a repeating expression, make a substitution. Let's set y equal to 2 to the power of x. This single move transforms an exponential nightmare into an algebraic dream. Let's recall our equation from before the substitution. Now we can rewrite it using our substitution. We replace every instance of 2 to the x in our equation with this new, simpler variable y. And just like that, the intimidating exponential equation has transformed into a much friendlier cubic polynomial. To find the roots of a polynomial, the standard strategy is to set the equation to 0. So we need to move the 130 over to the left side. Subtracting 130 from both sides gives us our standard form. So how do we find the roots of this cubic? We can use the rational root theorem. Here's where the rational root theorem becomes our strategic weapon. If this cubic has any rational roots, they must be divisors of the constant term 130. That gives us a finite list of candidates, plus or minus 1, 2, 5, 10, 13, 26, 65, and 130. Instead of random guessing, we test these systematically, starting with the simplest. Let's try 1 first. Testing y equals 1. 1 cubed is 1, plus 1 gives us 2. 2 minus 130 equals negative 128, which is not 0. So y equals 1 is not a root. Let's try y equals 2. 2 cubed is 8, plus 2 gives us 10. 10 minus 130 equals negative 120, still not 0. Y equals 2 is also not a root. Now let's try y equals 5. 5 cubed is 125, plus 5 is 130, which simplifies the expression on the left. And we get 0. Bingo! So y equals 5 is a root. Perfect. Since y equals 5 is a root, we know that y minus 5 must be a factor of our cubic polynomial. Now we need to find what it's multiplied by. Let's use polynomial division to factor out y minus 5 and see what remains. We know our cubic equals y minus 5 times some quotient polynomial q of y. Let's find q using synthetic division. Using synthetic division with our root 5, we bring down the 1, multiply by 5 to get 5, add to get 5, multiply by 5 to get 25, add to get 26, multiply by 5 to get 130, and add to get 0. The remainder is 0, confirming our root, and the quotient coefficients are 1, 5, and 26. So our cubic factors perfectly into y minus 5 times y squared plus 5y plus 26 equals 0. Now this equation is true if either the first part is 0, giving y equals 5, or if this second quadratic part is 0. But does the quadratic part give us any real solutions? Now let's analyze this quadratic part. To determine if this quadratic equation has any real solutions, we need to check its discriminant. If the discriminant is negative, there are no real roots. The discriminant is b squared minus 4ac. Plugging in the coefficients, we get 25 minus 104. The discriminant is negative 79. Since the discriminant is negative, this quadratic has no real solutions. Its roots are complex numbers, which don't help us here. This confirms that y equals 5 is the only real solution to our cubic. Therefore, y equals 5 is our unique real solution. Now we can finally solve for our original variable x. We're almost there. We found y equals 5, but the original question asked for x. So we substitute y equals 5 back into our definition. We have 5 equals 2 to the power of x. How do we isolate x when it's an exponent? We use the inverse of exponentiation, the logarithm. By the definition of logarithms, x equals log base 2 of 5. This is our exact solution. For a concrete sense of the answer, this is approximately 2.322. Let's plug our answer back into the original equation to be absolutely sure. Let's substitute our answer back into the original equation. This looks intimidating, but logarithm rules will make it crystal clear. We do have the second term is easy. When a base is raised to the logarithm of the same base, they cancel perfectly. 2 to the power of log base 2 of 5 equals exactly 5. That simplifies our equation significantly. For the first term, we need to be more clever. We need the base to be 2, not 8, to use the same cancellation rule. Since 8 equals 2 cubed, we rewrite it. Using the power rule for exponents, we bring the 3 down and multiply it with the logarithm. Now we use the power rule for logarithms in reverse. 3 times log base 2 of 5 equals log base 2 of 5 cubed. This gives us 2 to the power of log base 2 of 5 cubed. Since 5 cubed equals 125, again, we have a base raised to the logarithm of the same base. This simplifies to exactly 125. So we have 125 plus 5 equals 130. Perfect. Our solution checks out completely. 130 equals 130 with a satisfying check mark. This problem teaches us something profound about mathematical problem solving. What began as an intimidating exponential equation revealed itself to be a cubic polynomial in disguise. The key wasn't brute force or complex formulas. It was pattern recognition, seeing that 8 and 2 are related as powers of the same base. This is the essence of mathematical beauty, transforming the unfamiliar into the familiar, the complex into the simple. Every challenging problem is really asking us to see it from the right angle. And when we do, what seemed impossible becomes inevitable. Thank you for joining me on this journey through a seemingly simple equation that revealed its true complexity. Remember, mathematics is not just about numbers, it's about finding patterns and connections. If you enjoyed this video, please like and subscribe for more mathematical explorations.